that had appeared at the special point were 8 extra massless scalars. Now there are 9 scalars, of which one was massless everywhere in for every value of the radius, and the other 8 were massless at that special point.
Right.
And the gauge bosons, we had 2 U1s for all values of the radius.
Yes.
And 2 SU2s for that special radius.
Yes.
So 2 SU2s means we have 6 gauge fields, and so which is 4 additional gauge fields, and for 4 there are 8 helicity components. So for 4 of these gauge fields, each gauge field will eat one of just in comparison, will eat one of the Goldstone bosons, one of these massless modes. So that and they become massive by eating one of those, and what remains are 4 scalars, which are the Higgses. Is that right?
Right. Let's see. Let's see how that works. So, how many of these scalars actually remain? That's the first question. So we have these vertex operators. So first question is this. So we had these guys which were JL and JR. These were our 9 scalars. Now, JL and JR each had dimension 1.
Yeah.
That is why they were legitimate vertex operators. Doesn't matter that they had dimension 1. What mattered was that they each had equal dimension.
Yeah.
So that dressing with an e to the pi k dot x could shift both their dimensions to 1. This the first question we would have to ask is, away from this this special point, how many of these scalars continue to be legitimate fields? Okay, so we have these things which were what were the n and w is equal to plus minus 1 plus minus 1. And so that gave n and w equals plus minus 1, gave one of these JLs. Okay, these JLs were plus 1 plus 1, minus 1 minus 1, and del x. These were plus 1, minus 1, minus 1 plus 1, and del by x. Okay, so the first question would be, which of these survive as fields, massive or not? Okay, so which of these label vertex operators in the theory or not at all? So these would be things such that. So now let's look. Let us remember what L0 and L0 bar were. L0 was equal to alpha prime PL squared by 4. L0 bar was equal to alpha prime PR squared by 4. And PL was equal to N by R plus M plus W R by alpha prime. PR is equal to N by R minus WR by alpha prime. Okay. Let me now see. Why don't you guys do this? Do you mind doing this exercise carefully? You have to check which of these remain fields in the bulk.
I see. No, what do we mean by remaining as fields?
Remain by fields meaning are legitimate vertex operators. Legitimate vertex operators obey level matching.
Okay.
Okay? E to the power ikx doesn't change level matching because it has L0 equals L0 bar. So L0 has to be L0 bar. Okay? If L0 shifts and L0 bar shifts, that's fine. That just means that the operators become massive. But it remains a field. Now the Higgs mechanism eats up some fields. Some fields that were in the scalar sector are just not fields anymore. And the remaining fields are massive fields. Okay? So what you have to check is that the number of non-Eaton fields or the number of Eaton fields is equal to the number of
extra the scale the gauge bosons.
Gauge bosons that have gone massive.
Massive.
As you say correctly, the number of gauge bosons that have gone massive is 4.
Yeah.
So you have to check that the number of Eaton fields is 4. And then you have to identify the non-Eaton fields.
I see. And with and there we'll find that some of them might be legitimate fields and some of them might not be.
Well, anything that's not a legitimate field is just not there.
Okay.
That's Eaton.
I see. Okay. Okay.
Okay. Anything that's a legitimate field
I see.
is some field in the spectrum.
No, I mean just in terms of counting, is it right that we'll have 4 Eaton fields and
Yeah.
of the 8, 4 will be
4 should be Eaton, 4
Higgs.
should be not Eaton. Yes.
4 should be, I mean, just physical Higgs, so to speak.
No, wait. 4, yeah, right. There should be of the whatever 9 fields.
Yeah, one remains massless, one is an exactly flat.
One is the exactly flat
and that
direction.
I'm discounting from.
Right, and there should be 4 other fields that are not exactly flat, but parameterized directions in which you could move that were not pure gauge, but along which there are masses. Okay, so you should see 4 legitimate fields
Okay.
other than the one that you've discarded.
Okay. Yeah.
Okay, and then 4 of these should just go away. That's the Higgs mechanism. These guys are just Eaton. Okay, why don't you try it and we can discuss it because we'll spend time. Okay, fine. Okay, now something that I wanted to say that we didn't say in words before is this, that we got this new enhanced gauge symmetry at this self-dual radius. This is actually not a new phenomenon. It's a phenomenon we saw before at the end of the last semester. In fact, in much more complicated situations. I wanted somebody's help in reminding us where we saw this phenomenon.
Could you please repeat?
The phenomenon
Yeah.
of seeing enhanced gauge symmetry at special points was something we saw before, or is closely related to something that we've seen before at the end of the previous semester. I wanted somebody's help in reminding me where we saw this before. We've done this in a lot of detail now, but we talked about some similar phenomenon at the end of the previous semester. What? Do you remember when we discussed the heterotic string? We talked about lattices of compactified bosons. And we discussed that when the lattice vectors were root vectors of a group, then associated with every such lattice vector, we got a new gauge boson. Do you remember this? This is how we got E8 gauge symmetry for the heterotic string. Or this is how we got SO32 times E8 times E8 or SO32 gauge symmetry. Okay? Actually what we have here is a baby example of that phenomenon. Because you see, in this case, the left moving and the right moving lattice is just one dimensional, because we just have these lattices of PLs and PRs. Okay? But adjusting these L and R to the self-dual radius made the lattice with the right, it's just a lattice like this, right? Okay, let me say it more clearly. We had let me give you a 2-minute reminder of that story. Okay. I'm going to give you actually we talked about much of this then, but not in as much physical detail. I just want to connect this to that discussion. Do you remember we talked about how you can think of possible lattice compactifications, possible compactifications in an abstract way? We talked about how the vertex operators could be e to the power I kl xl and e to the power I kr xr. Okay? Then we talked about how the set of allowed KLs and allowed KRs was not arbitrary. The first thing that we required was that if any KL is allowed, if any KL and KR is allowed, then if KL1 and KR1 is allowed, and KL2 and KR2 is allowed, then KL1 plus KL2 and KR1 plus KR2 is also allowed because of the OP. Okay, this tells us that the sets of KLs and KRs form a lattice. Okay. The second thing that we saw was that the set of allowed vectors should have mutually local operator product expansion. Okay. Now you remember that if you have e to the power I kl1 xl times e to the power I kl2 xl, then this gives an e to the power I minus, then 2-point function has a minus, alpha prime by 2. So plus alpha prime by 2, KL1 KL2 log z, and we get a similarly minus alpha prime by plus alpha prime by 2 KR1 KR2 R2 log z bar. So this was z to the power alpha prime by 2 KL1 KL2 times z bar to the power alpha prime by 2 KR1 KR2. You remember this? Okay. Now what we want is that as we take one operator around the other, it's single valued. It vanishes. But this picks up a 2 pi, this picks up a minus 2 pi. So we required that alpha prime by 2 into KL1 KL2 minus KR1 KR2 belong to integers.
Even in self-dual.
Right. The self-dual will come later. That comes from.
This is even.
Right. Right. So then we had some convenient normalization where we absorbed some alpha primes. Okay, I'm not going to remember all the details, just remind you. So this was one condition on the set of lattice vectors. Then we looked at the modular invariance of the partition function. And we found another condition, that of self-duality. So we concluded that the set of allowed lattice compactifications was the set of even self-dual lattices, okay, where the inner product for measuring whether something was even or not, okay, was given by this inner product. Dot product on the left minus dot product on the right. When we were discussing the heterotic string, we had only left movers, because in the heterotic string we had left moving part with 16 dimensions needed to be compactified. The right moving part was just the superstring, so it was on its own trip. And then we looked at 16 dimensional even self-dual lattices, and we had this nice theorem of mathematics that there were only two such. Okay, these two such lattices were associated with E8 cross E8 and SO32. Okay, you remember we looked at we looked at the weight lattice and then some coset of it by two things, some coset that included the root lattice and one more thing for the SO32, and it was easier for the E8.
I was not present.
You were not present. Okay. Okay, but a central point in that discussion. Okay, a central point in that discussion was that when we landed up on this nice lattice which included root vectors of a group, every time we had root vector of one of these semi-simple groups, there was some condition, right? There was root square equals 2 and root square equals 1. Remember, we had some confusion about that. Length, long roots, short roots, or some complicated stuff. But anyway, for the groups that we were concerned with, everything worked. Every time we had a root vector of one of those groups, the e to the power I KL was a dimension 1 operator. And therefore, by the same mechanism as we discussed here, by coupling with the del of x on the other side, gave us a gauge boson. And there we got enormous enhancement. Right? We got these huge groups, these E8 group or SO32 group, some huge group from that construction. Here we are seeing a really baby version of this. Okay, and let's just take 2 minutes to see how what we're seeing is a baby version of that. What we did was to fix to the self-dual radius. Okay, we fixed to the self-dual radius, and at the self-dual radius r was equal to square root of alpha prime. So PL here was just 1 by square root of alpha prime times n plus w. Okay, and PR was 1 by square root of alpha prime times n minus w. Okay. Now just add this, actually this part of the algebra works whether we have the self-dual radius or not, but I'm just working it out for the self-dual radius because it's easier. Okay. First thing we're going to do is to check that this condition is maintained. That this KL minus KR alpha prime by 2 is an integer. Okay. So suppose we take N1 W1 and N2 W2. So if N1 plus W1, the whole thing squared. Sorry, N2 plus W2 minus N1 plus minus W1 into N1 minus W2. N2 minus W2. Thank you. Alpha prime, but we're supposed to then multiply it by alpha prime by 2. And the point is that the part that does not cancel comes with a 2.
Yeah, 2 into N1W2 plus N2W1.
Exactly. 2 into N1W2 plus N2W1 by 2. So alpha prime also cancels, so you get this. And actually, though we did it for a particular value of the radius, since only the cross terms survive, the radius actually cancels out. So it actually works for every value of the radius. Okay, so this is the first thing. This was the check that we have these that this even condition is obeyed. Okay, of course it had to be because it was obeyed by physics. Okay, this was the check. The even condition is obeyed. The self-dual condition I won't check for you, but it's also obeyed. Now the last thing about it was this business. The last thing about it was that let's look at the the point was that we obtained a gauge boson whenever one of our lattice vectors had PR squared equal to 0 and PL squared equal to a special value. That was the value of the root. Okay? That is exactly the condition we asked for last lecture. We asked for KL squared by alpha prime KL squared by 4 is equal to 1 and KR squared is equal to 0. So this gave us 0, so that could be, so you could have a del x and a KR squared, okay, this equal to 1. That was the same condition we had when we were looking at the heterotic thing. We put some particular value, we had some funny normalization. This may have become a 2 with that normalization, but when we put back the alpha primes, it was the same thing.
Just to repeat, these conditions ensure that the lattice is self-dual and even.
No. Lattice is self-dual and even is something separate. But this condition ensured that for this value of that root vector, for this value of that lattice vector, there is an associated bulk gauge boson.
Okay.
These were the roots in the root lattice. In this case, the roots are just two particular values, right? They were the ones with n and w is equal to, let's say, 1 and 1 and minus 1 and minus 1. So this root is just in this NW plane, this guy and this guy. So what group has a root lattice like this? Forget the tilt, that's not important. Of course, it's SU2, that's the positive root and the negative root. So what we've got is a lattice here which includes in it the root vectors of SU2. And that's why we got these SU2 gauge boson enhancement. We got a root part in the PL squared, in the left moving square and the right moving square. Always fixing to those values of n and w so that PR squared was 0 or PL squared was 0. That was what was completely special. I mean, both these things were special about the self-dual point. In general, even if you manage to produce, some tuning here and here so that this is equal to 1, if the PR square correspondingly is not 0, that will not correspond to gauge boson. In general will not correspond to any field at all because it will not obey level matching. Okay? Okay, excellent. So that's basically what I wanted to say. What I wanted to say was that this emergence of the this gauge symmetry, this SU2 gauge symmetry, we've actually seen before, perhaps more hurriedly and less detail and less with less physical understanding when we study the heterotic string. But I want to tell you that it's the same phenomenon, or really at least a very closely related phenomenon. It's slightly different because there we were talking about a purely holomorphic lattice. So this PR squared wasn't bothering us. Okay, slightly different but very closely related. Okay, fine. Okay, that's all I wanted to say about this. Polchinski has this discussion of compactification of several dimensions. Now this discussion, at least briefly, we went through in preparation for our discussion of the heterotic string. We talked about how this could be generalized to many things. And do you remember we talked about the physical interpretation of the number of parameters, including the B mu nu Wilson loops? Does anyone remember this, or am I remembering wrong? Let me remind you. Did we or did we not go through the canonical quantization, including zero modes of B mu nu?
I don't think so. No, not B mu nu.
We didn't go through that?
No.
I'll just remind you of it again because I thought we did, but maybe we didn't. We looked at these Narayan lattices, This we did, right? We counted the number of parameters. And did I give you an interpretation of the number of parameters from canonical quantization? If not, we should go through that. That's very important. No? I somehow feel. Okay, if not, clearly you guys don't remember it anyway, even if we did go through it. So let's quickly go through that again, or go through that if we haven't. Okay, so there is one, what I wanted to tell you about was that there is, when you compactify two or more circles, there is one new phenomenon that is qualitatively invisible when you compactify only one circle. I thought we discussed that, maybe we didn't, I can't remember. What? We did but very briefly. Okay, but let's do it in more detail then. Okay, so consider compactification of m directions. Okay, so we have xi goes to xi. Now, there are 2 or 3 new phenomena. One is sort of, you can guess, and the one is qualitatively different. So, you see, suppose we've got lots of xi's. What we can do is some sort of diagonal compactification. Just like when we were talking about the torus in Riemann surfaces. The torus, the most general torus, wasn't just identification this way and this way. We could have had a compactification like this. Okay? Now, when discussing the torus, we sometimes adopted one of 2 different points of view. One was to keep the metric eta,
yeah,
and slant the compactifications.
yeah.
The second point of view was to keep the compactification just 2 pi and 2 pi.
Yeah. But change the metric.
But change the metric to any constant k. Let's use that second point of view. Okay? So what we're going to use is that all xi's are equal to xi plus 2 pi. But our metric is going to be 1 over 4 pi alpha prime d2 sigma del alpha xi del alpha xi. Sorry. J, Gij. Where Gij is an arbitrary constant metric. Okay? By varying over all metrics, we generate the full set of geometrical toroidal compactifications.
And GIC will have the information about all the complex structure moduli.
Everything, including also about the volume modulus, right? Not just the complex structure,
Yeah.
so the Kähler part. However, the great thing about string theory is that this does not exhaust the set of toroidal compactifications. This was sort of obvious. If I'd given you 5 minutes to think about it, you would have come and written down this Lagrangian for me, and we would have all been happy. But this does not exhaust the full set of compactifications, of toroidal type compactifications, because in addition to this object, string theory also couples to the B field,
higher form field.
the B mu field. And the coupling to the B field, we have to discuss this in detail at some point.
Some Wilson line like things with non-compact, with compact direction, which will give us some scalar.
Very, very, very much like that. Let's see. Okay. So we have, in addition, we have d2 sigma. Okay, and then 1 by 2 pi b epsilon alpha beta del alpha xi del beta xj. Maybe we want a 2 here, times bij. Okay, You may ask, why did I put a 1 by 4 pi alpha prime here and not here? Well, of course, that's a choice of normalization of our Bij. But this is normalized so that the coupling of,
Yeah, vertex operator will have the.
right, that the coupling of this is simply integral B. This is a complicated way of writing that given how the string is moving in space-time, you just take B and integrate it as a 2 form over that surface. Just like a charged particle, the world line of a charged particle interacts with an electromagnetism through its world line action being integral A. Now this is sometimes written more complicatedly as A mu dx mu by d tau dt d tau. But of course this d tau cancels this d tau, it's just A mu dx mu, which mathematicians write as integral A. Just integral of the one form over that line. Okay? That's the natural coupling of a gauge field to a world line particle. Similarly, there is a natural coupling of a 2 form to 2-dimensional surface, just integral B. And just like this is this, that is that.
Yeah.
Okay? It's just the 2 form B restricted to the world sheet and integrated over it. For a mathematician, that's a much more natural way of writing that than this complicated looking thing. And this 1 by 2 pi is put for some reason. Okay?
And, the dilectron part is already in the Gij part, right? I mean, if the scalar coupling, if there's any, or I mean, isn't there some R phi?
There's integral phi
Yeah.
r.
Yeah.
Okay? That is separate. Okay? This we don't care about at the moment because our world sheets are flat. Let's say that we're doing canonical quantization on a cylinder. This will not affect it. The main role of this, at least if phi is a constant, in string theory is just to give the right sort of G for every genus. Okay? If you've got a phi varying, then that has more important implication, which a little bit we saw when we saw the linear dilettron theory. Okay? But this will play no role in our discussion at the moment. Okay? So let's forget about it. Okay. Now, I want to understand how this string theory here is, how it's different from the uncompactified string theory. Okay? As in the previous situation that we studied, all differences are just in the zero mode sector. Oscillators are untouched. Because all of this for oscillator part, just doesn't make any difference.
Some very heavy modes.
No. It's not about.
Okay, this is not a KK reduction.
Yeah, it's not about energy scale.
Yeah.
It's the fact that xi goes to xi plus 2 pi is a statement just about the zero mode.
Right.
So the oscillator parts are just totally unaffected. We will see in a bit that this B here. Okay, let me work out one thing. That's important. This coupling of the B field to the world to the string world sheet has an interesting. Okay, we will be interested in constant B, but in general, if you've got an arbitrary B, this remains the right coupling. Integral B on the world sheet. Now, I want to show you that if B goes to B plus dA, then this coupling doesn't change.
Yeah, this is gauging very.
This is totally obvious if you do it in the mathematician's language. Because if you do it in the mathematician's language, this is integral B, which goes to integral B.
Integral dA by Stokes theorem.
Integral dA, exactly. Okay? And this integral dA by Stokes theorem is integral A at one end, A at A at the boundary, whatever.
Yeah,
And if you've got some world sheet without a boundary,
For small diffusion, for small gauge transformations, this will.
If exactly, if you've got some well sheet without a boundary, and your gauge transformations are reasonable gauge transformations, as you said, okay, this will make no difference. So, for this reason, you might think that Bij equals constant makes no difference to the string. Why is that? That's because if I have Bij is equal to constant, let's say little Bij, that can be generated with Ai is equal to Bij xj. Where little Bij is some antisymmetric guy, maybe with some 2's. Okay? So d of this will be this. Okay? And so this Bij constant is pure gauge. And so it should not affect string theory at all. But let us be careful. This is absolutely true when X is non-compact. But when X is compact, we have to be careful. Because the gauge transformation we have to do is, in general, okay, the gauge transformation we have to do is in general not single valued. Right? Because when X is compact, X and X plus 2 pi should give us the same thing. But we're performing a gauge transformation which at X, at 0 gives us 0, but at 2 pi gives us 2 pi times Bij. Okay? So unless Bij is something very specific, okay, this quantity is not, it's not obvious that this quantity is a legal gauge transformation. So when X is non-compact, this is pure gauge. The gauge transformations that we have to perform to get rid of it are okay. They affect nothing. And this doesn't affect string theory at all. Constant Bij. But when when the spacetime is periodically identified, this argument is no longer good. And we have to be careful. Okay? But once again you see that everything interesting that could possibly happen could only possibly happen in the zero mode sector. Okay? You can check more, you can check, if you don't like this argument, we can check explicitly that if you put in the oscillator expansion here, this term just vanishes. For the oscillator parts, this term just vanishes. You can check that explicitly. Okay? It will not affect the oscillator parts at all. This whole term here is oscillators are unchanged, and everything interesting happens in the zero mode sector. Okay? So we're going to focus our analysis on the zero modes. Is this okay? So now, when we look at the zero modes, what are we supposed to do? We're supposed to do the following. Xi is equal to Wi sigma, okay, plus Ni, okay, plus something, plus pi tau. In fact, what is it? What was it? Alpha prime pi tau. I keep needing to do this again. 1 by 2 pi. 2 pi cancels. 1 by 2 alpha prime x dot square. So p is equal to x dot by alpha prime is equal to p. So x dot is equal to alpha prime p. So alpha prime pi tau. Okay? What exactly can we say about these alpha? What exactly? Okay, this part is clear. Clear that Wi is an integer. Because when sigma goes by 2 pi, you have to come back modulo 2 pi. What can we say about this guy? Now we have to be a bit careful. Because what we can say is the following. Actually, let's be a bit careful. Let's just put some zeta I tau. Let's just put some zeta I tau for a moment. What we have to do is to identify what the connection with the between zeta I and the canonical momentum pi is. Okay? So let's look here. In the 0, 1 sector, what does this become? This becomes alpha prime d tau, so 2 pi goes, so 2 alpha prime gij xi dot xj dot. Obviously. What about that guy? That becomes 1 by 2 pi. Now, let's see. Epsilon, let's say our epsilon is such that epsilon 0 sigma, tau sigma is 1. So, if I'm interested in, okay, so this becomes, look, this becomes d2 sigma. So once again we can get rid of the 2 pi. This becomes xi dot del sigma xj minus the other way around. But then, okay, let's write it out carefully. So minus
xj dot
x dot del sigma xi bij. Okay. Now we, yeah, exactly. Now we just plug this in. So this is xi dot, and this is wj. This is, wait, we'll come back to this in a moment. Yeah. Plus xi. I want to compute the canonical momentum, so I want to keep it free right now.
Yeah, I mean the x dot should be made explicit.
Yeah, exactly. Xi dot wj minus xj dot wi bij. There was a by 2. By 2. But because bij is antisymmetric, this is the same as xi dot wj bij. This is the Lagrangian. Now, so the full Lagrangian is this plus that, which is 1 by 2 alpha prime d tau, this also d tau, gij xi dot xj dot. Now the canonical momentum is what? It's, so pi is equal to gij pi alpha prime xj dot plus wj bij. Why does the first term only have dots? Okay, it's true. It has the other part as well, but as far as computing canonical momentum is concerned, the other term does not matter because that term has no dots. So that's plus gij wi wj something. Okay, and this term will be important in computing L0 and L0 bar. It's the analog of the w squared term we had. Yeah, thank you, it's there, but it's not going to be of importance to me for this purpose. Okay, this is the key point. The key point is that the canonical momentum is not unaffected by this bij. The relationship between x dot and canonical momentum is altered. And where have I missed out? No, this is correct, right? Is altered by the presence of this bij. So now what is quantized?
Yeah, pi's and I mean the p and x.
P is quantized,
yeah.
right? P is the guy. It's this pi.
The commutator is pi and x.
Exactly, because we're going to have e to the power I, whatever, e to the power I kx, and this k is quantized, and k is the eigenvalue of the thing that has canonical commutation with x, which is canonical momentum, not mechanical momentum, right? So this pi has to be equal to ni, because our compactification was 2 pi. Okay? And therefore we conclude that this quantity is an integer. Okay? And now if we want to know what xj dot is, we have to solve. So xj dot is equal to ni minus wj bij into alpha prime gij.
J will be raised.
Yes. Okay? What?
It's okay.
J, okay, P, R, X, I, blah, M, I, okay. All good. M. Okay. And therefore we get that this is equal to alpha prime nm minus wj bjm gmi times tau. This is the zero mode part that we need to plug in. Okay? Now we can go through the full discussion that we had earlier with one boson and one fermion. Okay? We can go through the full discussion with one boson, with one compact direction. The really important point is here to ask how many different compactifications, how many different toroidal compactifications we have here. So can you count for me if we've compactified m directions, how many different distinct compactifications do we have?
No,
What do you mean by distinct? Oh, distinct now.
Distinct space-time toroidal compactifications. They're labeled by GIJs and BIJs.
N square.
And m square, exactly. So if we compactify m directions, we have m square different inequivalent compactifications. When m was 1, there was just one, labeled by the radius of the circle. When m was 2, geometrically you might have thought the answer would be 3, because there's the size of the first guy, the size of the second guy, and the angle. And number in GIJ is 3. Symmetric two-dimensional tensor. But there's one BIJ as well, and that makes it 4. In general, in m dimensions, the number of inequivalent toroidal compactifications is m squared. This, by the way, is the result that we also got when we looked at Narayan lattices. I don't know if you remember, but we did some coset business, right? It was the coset was this. It was SOM, M divided by m/SOM because the space of, when we had, you remember the condition for a lattice to be even and self-dual was some condition on dot products between lattice vectors. So any transformation of the lattice that left dot products invariant gave you a new lattice. That was this SOM comma M transformation. But then we argued that those transformations that acted left moving by only on left movers or only on right movers were trivial. They affected no physics. So that was the modding out. Okay? And then we counted the total number of parameters. The total number of parameters in SOM comma OM is 2m into 2m minus 1. Because you just think it's same as the number of parameters in S of 2m. Okay? And then number of parameters in each SOM by 2, right? And the number of parameters in each SOM was m into m minus 1 by 2, but then there was a 2. So we got 2m squared minus m squared plus m, which was equal to m squared. And this m squared is the same as this m squared. Okay? And the history of this went that Narayan, who was then a very young physicist, did this abstract conformal field theory business, wrote down his lattices, and computed that there were m squared inequivalent lattices, and said that, but if you look at geometrically, the answer looks like m into m plus 1 by 2, which is less. So we found new consistent string theories that have no obvious geometrical interpretation. And then Narayan, Samadhi, and Witten corrected that. They gave the obvious interpretation. It's simple physics. Okay. See, the additional parameters for this came from the Bij. Okay. Now, there is some interesting physics when we try to do T-duality in the presence of both G and B. And we should discuss that, but I'm wondering if I'm going to have to go very soon. So I'm wondering if today. Today. Okay, I underestimated what we would work out today. I thought we would briefly talk about this and talk about orbifolds. We're certainly not going to get to the orbifolds. Will we get to? I think forget it. Let's not rush this. I'm sorry, I'm going to have to go in like 6-7 minutes. So let's not. Okay. So next class, what we will do is we'll complete this discussion. We will then discuss orbifolds. Let me tell you 1 minute about orbifolds, so that it's not new to you next time. Okay, this is what I really thought I would talk about today. Okay, okay. Let me just say one minute, and then we continue next class. Okay, what we did was, when we looked at compactifications, we looked at x is equal to x plus 2 pi. We looked at modding out our theory. There was translations in x was a symmetry of the theory. We took a discrete subgroup of that and modded out our theory with that. Okay? We gauged our world sheet theory with this discrete subgroup of an existing symmetry of the theory. This is clear, right? Now you're going to ask, can we play this game again? can we gauge our world sheet theory with, can we gauge some other global symmetry of our world sheet theory? Now there is one obvious global symmetry. See, global is as opposed to something like something that depends on sigma. When we try to do the orientation reversal, again we were gauging by some symmetry, but that from the point of view of the world sheet was not a global symmetry. It was a space-time symmetry because we flipped sigma, which was the space coordinate of the world sheet. Okay? From the point of view of the world sheet, we're looking at, we're searching for global symmetry. Now, in this free boson conformal field theory, there is one other obvious global symmetry, and that is x goes to minus x. Okay? So what we're going to do in next class is to study the theory when we gauge x goes to minus x. So the configuration with x is to be identified with the configuration with minus x.
What will be the gauge field?
No gauge field. Was there a gauge field corresponding to circles? You see, when you gauge discrete symmetries, there are no gauge fields. Continuous gaugings require gauge fields. Gauge just means identify configurations.
Global symmetries.
Yes, this was discrete global symmetries in this case. Okay, now I wanted to just to give you 2 minutes of geometry, and then we stop today's class. See, in space-time, what makes string theory interesting, what makes world sheet string theory interesting is this constant interplay between the world sheet and space-time. Okay? So from the point of view of the world sheet, x goes to minus x is some global symmetry. But of course, x was not any old thing, it was a coordinate in space-time. So what's actually happening? If x is going to be identified with minus x, it means that space, which we thought was infinite, actually has a wall. You go here, you can't go further, because going here is the same as bouncing back. Okay? So we're going to ask, can we put walls in string theory? Now, walls are very interesting, but the universe that we see around us, a non-compact 4-dimensional space-time, doesn't appear to have any of these walls. So these things will be most interesting when done in the compactor directions. Okay? So the most interesting, we will mainly be interested in these walls when they're done in compact directions, and the simplest compact direction is a circle. So what we're going to do is to look at also, apart from just a wall in non-compact space, we're going to look at x goes to x plus 2 pi, gauging this, so making it a circle, and also gauging x goes to minus x. Okay, now can somebody tell me what happens to geometrically in space-time? What are we doing?
We are identifying a semicircle. Our fundamental domain is some semicircle.
Right, semicircle. Exactly. It's an interval.
Yeah.
Exactly.
Yeah, in the sense.
Yes. Yes. Half of the circle. Exactly right. Okay. You can see it this way. Suppose we've got this line, and we're identifying let's say minus 2 pi, 0, 2 pi, and so on. So these points are identified, but these points. No, it's not only changing length, because you see around this point something is identified.
Yeah. And
So this point is a
reflection.
right. So let's first find are there places where the identification is a fixed point?
0 and pi.
Exactly. 0 and pi are fixed points. Why are they fixed points? Because under reflection 0 maps to 0, that's a fixed point. Under reflection pi maps to minus pi, But because of the circle identification, pi and minus pi were the same point. Okay? So, we should think of this not as 0 to 2 pi, but I mean, it's more convenient to think of this as minus pi to pi. So, this whole circle has been halved because whatever's happening here is the same as what's happening here. And the two endpoints of this interval have fixed points. Is this clear? Now, in this situation, so now the theory does not live on a circle anymore. It lives on a line with two ends. Okay? And as we will see when we study string theory in such a space, of course, modes can move around here. But there are also modes that are stuck here and modes that are stuck here. Why is that? Why is this? It's because, you see, when we quantize the string, as our string goes from 0 to 2 pi, it has to come back to the same configuration. But something here is the same as something here. So we will be able to quantize, one set of new modes that was absent without this identification. It's just that if something starts at some point at 0, it ends as when you come by to 2 pi at minus that point. Now that, of course, is a string that looks like this. All such strings, if they move far away, if this point moves far away from this thing, it costs energy. It has to stretch the string. So these are states that are localized around here. The states localized around here. And then there will be the normal states that are free to move around here. Okay? We will discuss this all in detail next time. Okay? These are very interesting things, these orbifolds. Okay? And then we will understand what happens to orbifolds under T duality. We'll understand how it happens. We have a lot of fun now.